So this piece of work spans a lot of years. What's really interesting is where we are lately about it. I'll try to squeeze that in. I might have to go a little overtime to do that. So this paper here will appear in a legacy for Victor Lomonosov. It came about in a funny way. We were preparing work on commutators, me and my co-authors, these co-authors, and I gave a series of lectures on it, and the core ideas were about this universal block tridiagonalization. And Shuang Zhang and the C-star algebraists at my department didn't believe it for a couple of weeks. And so I talked to them and I talked to the people, and Shuang suggested this should be a standalone thing. And so we split our work from commutators into two pieces. This is the first piece, and this is going here. And you can see it already in the archives if you like. And the second piece will probably be in the archives in the next month or two. Okay, so anyway, I'll try to give you the main ideas that drive this rather than so much the details. So here we start. First of all, what is B of H operator matrix sparsification? I've seen the term sparse matrix for years, but I was never sure exactly what the definition was. But this is mine, and I'll do it by examples. The spectral theorem for compact normal operators. You can go from a full matrix of representation to a diagonal matrix. That's a great sparsification. Now, what about an operator with a cyclic vector? Okay, well, if there's an invariant an operator with invariant subspaces, then every vector is cyclic. And in every vector, you can generate an upper Hessenberg. That's what they look like. So the diagonal and the lower diagonal are supports and everything above the diagonal. So they look upper triangular-like, okay? And if you don't have a cyclic vector, you can still take sort of direct sums, and you get this direct sum of upper Hessenbergs and stuff on top and zero on the bottom. So it's block upper triangular with Hessenbergs down the diagonal. So that's kind of interesting. There's a little proof. It's not the main idea. The main idea is this, and I heard this first that I remember from a Joel Anderson lecture in '76, which was seminal for me. Okay, and in it he showed us how if you got a cyclic vector self-adjoint, you just use the upper Hessenberg idea, you flip it, and you get a tri-diagonal matrix representation for that self-adjoint. If you want to do it for the whole space, okay, and you know it's not a cyclic vector, but an arbitrary self-adjoint vector, then you can repeat this, the proof of this in segments and flip. The Hessenberg thing will give it to you. So when you flip, you'll get really just tridiagonal direct sum of tridiagonals. Okay, good. Why is this interesting to us and to me originally? Here's the first application. It's about a 4x4 matrix problem. And before I say this, I want to explain two different perspectives. One of the most famous results in the area is Joel Anderson's work on commutators. I mentioned it later, but I should mention it here instead. Okay, the Pearcey topping problems, there's a list of them. The main one is still open, which is every compact operator a commutator of compact operators? The key test case was getting the rank 1 projection as such. And Joel Anderson could do it. That's after I tried for about 6 months. So I listened to that lecture. And what he did is he targeted this rank 1 projection matrix with a 1 in the corner and zeros everywhere else, and tried to find an A and B. And he was kind to himself. He chose A and B not to be tridiagonal because you can prove that can't work. But he chose it to be tri-block diagonal with the central block 0 and the off blocks rectangular n by n plus 1s and vice versa, n plus 1 by n's. And they were diagonal-like. So they just had one string of diagonal-like entries. And he was able to solve that. And then he could use that to show that every compact operator was a commutator of a compact with a bounded. But nobody since then can get two bounded operators. At that time, I asked the problem, maybe you couldn't even get strictly positive operators, ones that didn't have a kernel, because he did have a theorem that if you had a large enough kernel, then you could do it. Okay, so the kernel became an issue. I decided get rid of the kernel and ask the question. I'll discuss that more later. Anyway, there were two sets of problems that interested me. That one and the Hilbert-Schmidt version. Is every trace class operator with zero trace a commutator of Hilbert-Schmidt's? And after a year's work, these became seminal questions. Could you solve this commutator equation with these three operators? The first two are easy, but non-trivial a little bit. And the third one lasted for 3 years. And this is what happened. And it was the beginning of being interested in these, well, first staircase forms, then this universal block tridiagonalization. And it is universal, which Gido and Zhang and some of those other people were wondering whether this would work outside of B of H. It does work outside of B of H in unbounded matrices, but we're not sure to what extent it will work in C-star algebras, possibly approximately finite, things like that it might work on. Okay, here we go. So if you check the norms of these things, the trace norm, okay, it's all two, they're all two. These were extremal problems in the finite examples that I first studied, okay? And if you check the trace norm, okay, you take the trace of both sides, you get 2, and use the triangle inequality, the Holden inequality, and you get is less than twice the product of the Hilbert-Schmidt norms. Divide by 2, and you get this condition. So I asked myself, maybe the thing is true, and you could get 1 for every size matrix, especially these test ones. The first one is very easy, the -1 matrix. The -1/2 matrix is tougher, but you can do it, and you can do it with product norm 1. But I couldn't get 1 for 4x4, and I put my friend Lade Watson on it in a linear program problem, and he came up with 4/3 as a lower bound for the -1/3 matrix. And with some work, I was able to actually get A and B that achieved 4/3. That was exciting, but I couldn't prove it because it was just a computer result. So it sat for 3 years, and then I heard about this tridiagonalization. So I went home and I said, no, I'm doing a different thing than Anderson. Anderson had an idea about what forms to target this D matrix in. I was trying to show that no A matrix will work, or a B matrix pair will work. So I needed to figure out, is there some general approach that could work, kind of like the tridiagonalization, but what would it tell me? So I decided to make this new list. It's a little funny. It's got 6 vectors instead of 4 in C4. Still, I want to make this list. And when you Gram-Schmidt it, you'll be able to span all of C3. This is important. Direct sums don't work. So you need to be able to get a spanning set. So I stick in these things at the end. When you do this, then you have A1, E1 star, etc. You get what you're seeing. Okay. Now, when you Gram-Schmidt this, you preserve the following phenomena. When you hit the verse vector, which is E1, with A, it's a linear combination of the next 2, even after Gram-Schmitting. And for the star of that, A star of E1 is a linear combination of first 3, even after Gram-Schmitting. Now, the second and the third may disappear. I call that collapsing. Then it's even a sparser matrix. But the key thing is the 4-1 and the 1-4 position. And I'll tell you why. Because without that, something bad happens. Let me tell you what good happens. You calculate the diagonal entries, and we're going to use the trace. And you get, well, in a way we are. You get 1 is equal to this thing, 1, 2, and 1, 3. That's shorthand notation for 1, 2 means A12, B21 minus B12, A21. This is linear algebra at the freshman level. Okay, so this is nothing. This is matrix multiplication. Then you get this funny lag phenomena. You get a cancellation for the next one. By the way, this new basis fixes E1. It fixes the unitary, fixing E1. So it doesn't disturb this minus 1/3 matrix. That's really terrific. So when you get this happening, you get this second equation and you get this third equation. Minus 1/3 comes in later as a lag. When you add them up, you get this last one. If you take the first one and you subtract from the last one, you get 4/3. Wow. 1, 2 plus 1, 3 plus 2, 4 plus 4, 3. Now, that's got some A's in it, but not all. But the important thing is they're all distinct. So like A12 appears only once in those formulas. If you didn't have those zeros, you would get duplication of A41, and none of this would work. So that's less than or equal to the sum of these products of ABs, and use Holder again, and you get the square root of the sum of some of the A squareds, some of the A's, and some of the B's. Maybe not all of them, but then you can fill them out and get the full Hilbert-Schmidt norm and A and B, and you get this inequality. Once that happened, I already had one where you get equality, and this problem is solved at the 4x4 level. Okay, now the universal block, the staircase form, which a precursor to that, that's what I'm going to get to soon, and then we'll get to the block tridiagonalization. But just to tell you where this one goes, this argument generalizes. So a few days later, with dinner with Ken Davidson and the lemma, I was able to attack the problem of these, what I called them, atomic matrices. I had shown in 73 that if you could solve the problem for these guys, then you could solve the problem for everything. So these became very important, and this is where the minus 1/3 and minus 1/2 and minus 1 matrices were born. The formulas worked out worse. They were sort of optimal, in a sense, for those special kinds of matrices. By the way, it was interesting, and it's always been interesting, how as you let the minus 1/3 get to be a larger matrix up there, okay, right there, it starts to look like the rank 1 projection operator, which was very hard, and that was Anderson's contribution. Okay, so from 76 to 2004, here were the contributors, and then there's this theorem. Before I get to that, let me just tell you what this result here was. So I had shared in 73 that the summation of log n dn, when the dn's were positive and added up to the d, that summation was a sufficient condition to guarantee that guy was actually a sum of Hilbert-Schmidt commutators, which was another question Pierce-G-Topping had asked. Okay, here I'm showing it's a necessary condition. And to do that, you need to expand a little bit on the block triagonal forms. I'll mention that expansion. Anyway, this result blossomed into work from Joel Anderson and Nigel. Joel Anderson was not related to the Hilbert-Schmidt problem, but blossomed into our recent work on Joel Anderson and the limitations of his techniques. I'll try to mention some of that. How much time I got? 14, okay. Well, let me try to get there. Okay, so one of the big results is a complete generalization to arbitrary ideals in B of H. The IJ commutators and the commutator ideal. We have answers to what that is. It's a self-adjoint space, clearly. And so we can characterize what they are. Why are they important? Because those are the domains of, those are the kernels of unitary invariant linear functionals, traces, even abstract ones on ideals in B of H. So it got to be a big deal from that and the characterization is it's a self-adjoint set. So all you got to do is characterize the self-adjoints, and the way you do that is you monotonize their modulus, and then you check their Cesaro mean, and you take that diagonal, and that diagonal has to be inside of the IJ ideal. is a way to multiply ideals and get a product ideal. It's kind of simple, okay, if you haven't heard it. So that is the characterization, and it's via Cesaro means. So you take the Cesaro mean of the given diagonalization of that self-adjoint. Okay. So there's these wide open problems I mentioned before. I won't stay on it. And then back in 2019 and 20, my co-authors and I created this universal representation to try to pursue more what's going on. First, the comment. What I learned from my C-star algebra folks is how important block tridiagonalization is in C-star algebras, and I'd seen it for a number of years, but it was always at the approximate level. So the first thing you ask is, what about just B of H? It's pretty trivial. In B of H, you just fix any central beginning block and just you expand the rectangulars to the right because there's a limited number, there's like K rows and columns, and you go out far enough so that you can control the tails, and you can make the Hilbert-Schmidt norm of what's left less than epsilon over 2, and then you do that again for the next central block, which is bigger, and etc. So you get an easy block triangulation up to epsilon over 2 perturbations. So this is really easy. But the point is that it's not exact and it's not universal. The block size grow depending on what happens to the tails of those L2 vectors. But what's interesting though, is you only need the vectors to be L2, the rows and the columns. You don't need the operator to be bounded. So this is even for unbounded kinds of matrices operators. Okay, so that says a lot of what you're saying. Now, let's get to the main sort of point, and it won't take too much longer, okay, to finish this and then add some perspective. This was the key thing, this list. It grew out of that other list. Now, there are two attributes about this list. This list is nicer if you got like a reducing sort of, what do you call it, a generating vector for A and A star. So you got this one reducing, so is the whole thing. If you can get the whole thing, then you get a sparser situation, but can't assume that. And there's a little bit of invariant subspace comments that can go in here. So that's worth talking about, but not now. Okay, so you want to make sure you're not in the situation of direct summing, but you cover the whole space. So you intersperse the standard basis here. And what you do is you then look at the first vector E1 and you apply A and A star to it and you list them. Then you list A2. And you've got this self-referencing sequence. Then you take A of the second guy, okay, and you list it next. And then A star of it. And then you list E3. And you keep doing it sequentially and you create this list. Now, if the list doesn't collapse, we can look at what this matrix after Grimm-Schmitting does. If it does collapse, we need an induction argument. I'll leave that out. It took a while to get a good induction argument. And we create from this the 369 case, 369 staircase case. So let's just check it. A of the first vector is a linear combination of the first two, as well as the Gram-Schmidt. So the A twiddle, if you will, A twiddle of E1. So the Gram-Schmidt second vector is a linear combination of first two. That gives you that first column. I have it labeled for you. If you like it, I can make it a little big. Oops, it's not going. There, it's a little bigger. Okay, then for A star, you can see that it's the first three. I guess I need to go up a little bit to do that. So A star of E1 is a linear combination of the first three after you Gram-Schmidt it. Okay, what about, let's go a little more. What about A of the second guy, A E1? That's A squared E1, and you can see it doesn't appear in the 4 position, but in the 5th position. If you keep going, you have the columns 2, 5, 8, etc., and the rows 3, 6, 9. And you don't even need boundedness for the A. All you need is that the words are defined at those vectors of the products of those matrices. So it's conceivable there are unbounded situations. You can give conditions on the range and domain of these A's that make this work. Okay, so anyway, getting back to the main story here. Okay, and the thing you needed to be able to solve both Hilbert-Schmidt problems, the finite linear combination problem and the single commutator problem, is to be able to do this on a finite collection of A's. And you can, but the stairs are bigger. And I want to talk more about it, other than instead of n times 3, you have n times 2n plus 1. The stairs grow like that. So I like to make it symmetric looking instead of asymmetric. But in the theory, that asymmetry that you see in the stairs actually can play an interesting role in certain spots. But for a lot of our main work, we just assume there are stars in the 2, 5, 9 situation. Okay, so that's universal staircase forms. And here's the proof for universal block triagonal forms. There's the proof. Now, you have to be careful, and you have to look at the, at the sizes of the stairs and see what they are and prove inductively that these are the formulas. And so I've drawn them for you, and those are the stairs. Let's focus on this first guy, the 2-1 block. Okay, that's rectangular of size 2 by 3. Okay, and we have a lot of interesting open questions about this staircase form for a single operator. And that is, can you have a change of basis and make it sparser? The answer is yes. That's the deeper stuff, and it's in our paper. You can take a look on the archives if you want. Let's go down a little bit. Okay, the off dice. Oh, by the way, this is not Anderson, because Anderson's blocks grew arithmetically. These grow geometrically, but they could be smaller. And if they're smaller, we can find obstacles to making Anderson's approach not work on some diagonals. I didn't mention the work, and I should, of Marcoux, Davidson, and Rajavi, and independently, Patnaik and myself answered my question about can you get a strictly positive diagonal as a commutator of compacts? And the answer is yes, but they were very rigid. They had multiplicities of 2, 3, 4 in that order. But then the question is, could you do it with these larger block trigonal forms? And yes, you can. And you can get similar things, but you still can't get everything unless you go to full exponential. There we don't know. But we can show that anything that grows slower than exponential, there are diagonals that you can't do using the Anderson model, which is what's exciting for us and the main thrust of the second paper. But this also, I think, gives hints on where you need to look to be able to solve the commutator equation, partly because if you have AB minus BA equals D, then you can block tridiagonalize all of them with the same block triagonal forms. And that turns the problem into a finite matrix problem. So you don't have to necessarily resort to infinite matrices to get this done. And maybe there's a slick induction to make this happen. And that's the goal, one of the goals of our paper. And that's it.
Okay.